Hello, so cell potential. We are going to be talking about the potential energy between the anode and the cathode. That is called our cell potential. So the difference between that energy between our anode, where oxidation occurs, and our cathode, where reduction occurs, is our cell potential. So it depends on the ease of oxidizing at the anode and reducing at the cathode. We call this our standard EMF. So standard EMF is where we have this not sign, right? Not means under standard conditions, 25 degrees Celsius, 1 atm for gases, 1 molar concentration for solutions. We would take the sum of the cell potentials of our half reactions and determine our cell potential, our standard EMF. We can write the shorthand notation for a cell by saying, so oxidation is always on the left. So oxidation is going to be over here. We're going to have our electrode, which is a solid, with a single line, which is a phase change, and whatever our electrolyte is. So that would be whatever is aqueous in our solution. We then have a double line. That means that we have a salt bridge, followed by our reduction. So the electrolyte that's being reduced, the single line to show the phase change, and then the electrode. So oxidation is always going to be on the left, so this is oxidation. Reduction's on the right. A single line is a phase change. So that would be, aqueous, solid. A double line indicates our salt bridge. So this is the reaction we looked at earlier. We know just by looking at this that the zinc is being oxidized because it's on the left. The copper is being reduced. Our electrode is a zinc electrode in a zinc solution, right? Copper electrode in a copper solution. Here's our salt bridge between the two. We can tell all that by looking at that shorthand notation. So if you were given this shorthand notation here, you would be able to draw this diagram because you know, right? The zinc's going to be oxidized. I'm sorry. So you could even write the zinc equation, right? Zinc solid yields zinc 2 plus 2 electrons. We know that. So you got your zinc in solution. We know our zinc solid is our electrode. It's a solid. It's a single line because then we have zinc in solution, right? It's separated by this salt bridge. We then have over here, we got a cathode that is copper. In solution is copper ions. We know it has to be connected with a wire with electrons going from left to right. We know all of this just based on this shorthand notation. So I could give you this shorthand notation and say, draw this cell, and you should be able to do that. So electrodes. Typically, at the anode, it would be made of whatever metal is being oxidized. At the cathode, it would be made of whatever metal is being produced by reduction. This is what is typical. Though sometimes we are looking at the oxidation or reduction of a gas. In that case, we would need to use an inert electrode. So this electrode doesn't participate in the reaction. It only gives us a surface for those electrons. So if we look at this half reaction, where we have manganese, is going from a +7 to a +2 state. We would need to use a platinum electrode because these manganese, as you can see, are both aqueous. Well, if they're both aqueous, that means we don't have something for these electrons, right, to come off of. And so we would need to use some inert electrode. So we can use a platinum electrode. Look, platinum doesn't even occur in the reaction. But we can use a platinum electrode that will store those electrons so that we can have that conversion between the +2 and the +7 charge. So what we have is we actually have a standard. We call this our standard hydrogen electrode. It helps us determine the potential difference between all of our other reactions. So we call this reduction of H plus to H2, we assign the standard hydrogen electrode as having a voltage of 0. Once we have a voltage of 0 for the standard hydrogen electrode, we can now compare everything else to this electrode. So the standard hydrogen electrode reduction potential is exactly 0 volts. So that means it does not take any energy. Therefore, any half reaction with a stronger tendency towards reduction would have a higher positive value for its E naught of reduction than 0. So it would have a more positive E naught of reduction if it wanted to reduce. If it wanted to oxidize, it would have a more negative E naught of reduction, meaning it doesn't want to reduce. So anytime you see a positive E naught of reduction, that means it wants to reduce. If it's a negative, it does not want to reduce. So if we look here at this reaction, as we can see, here are some E values. The half reaction that has a stronger tendency to occur has the larger positive half potential. So here, which one's more positive? Well, it looks like down here, this guy, this positive 0 volts, right? Because this one's negative. So this one wants to occur. So this is the one that's going to be reduced. So the reduction happens at the cathode. So this is going to be at our cathode, okay? The other one's going to be at our anode. Electrons are going to flow from one to the other, and we can figure out this voltage difference. It will actually be our cathode minus our anode. So we should get a positive 0.76. So which way are electrons going to flow? In this case, these are E naught of oxidation. Normally we do reduction, okay? Oxidation though, this one's more positive for oxidation. So this one wants to be oxidized. So the zinc would be oxidized and the copper would be reduced. So we want reactions to be spontaneous, right? Normally, we would figure out which one has the higher reduction potential, okay? So the higher on the table of standard reduction potentials, the stronger it wants the reactant to be reduced. The lower it is on our reduction potentials, the more it wants to be oxidized. So we do have this table of reduction potentials that you're going to use that I'm going to recommend you print out. I will put it in Wolfden so that you have it to print out. So here is our table. Let's take a look at this table. Anything at the top wants to be reduced. It is the stronger oxidizing agent, okay? So here we go. We got fluorine. Fluorine does not want to be a gas. It would prefer to reduce, right, into F minus, okay? These are all reduction reactions, okay? Reduction is the gaining of electrons. So you can see every single one of these is gaining electrons. So these are all the reduction reactions. So this one wants to be reduced a lot, right? So anything up here, any positives want to be reduced. As we keep going down, the one that's at 0 is our standard hydrogen electrode, right? Hydrogen. So we're going to compare everything to hydrogen. That has 0 voltage. Everything down here, it doesn't really want to be reduced, right? It prefers to be oxidized. So we can look at these, we can compare these and see which one wants to be reduced, which one wants to be oxidized. So we're going to use this chart a lot, and we're also going to use these voltages. So cell potentials are intensive properties of matter. That means that we are not going to multiply the E naught values, even if you multiply the redox reactions, okay? Their values are not going to change. These are always going to stay constant. So do not ever change the values. You hear me? Don't ever change them. The cell potential of an electrochemical cell is the difference between the cathode and the anode. So you would take E naught of the cathode minus E naught of the anode, and you would determine the E naught of the cell. Okay, that is our equation. They are both going to be reduction potentials, okay? So even though reduction is happening at the cathode, you're going to take the reduction potential minus the reduction potential of E naught of the anode, and you're going to get E naught of the cell. So these numbers here, you are never going to change them. Don't ever change their sign. Don't ever multiply them by anything, by 2, because you multiply the reaction by 2. No, these are your values. They are intensive properties of matter. So let's look at these. Use the tabulated electrode potentials to calculate the standard cell potential. Whew, what do we do? Gosh. Well, first, you should probably figure out what your half reactions are. So first, aluminum solid, right, is going to aluminum 3 plus. So we know that that wants to occur. That is oxidation. We know that based on what's happening. It is losing 3 electrons. So we write our oxidation reaction. This reaction might be a little bit harder to write. There is a little hint though. If you look back at our reduction potential chart, you can actually find that reaction on the chart. So it's actually right here. So even though it's not balanced when we do it up in the reaction, here it shows us what the actual balanced reaction is. So that's actually kind of nice. So here's this reduction reaction. As you can see, it's 0.96 is its E value. So let's see. 0.96, so we know reduction happens at the cathode. So that was 0.96. The anode, we would also find this reaction. So we would need to go back to our chart, aluminum, right? Find aluminum on our chart. Make sure you get the right one because there are different ones. So aluminum 3 plus 3 electrons, right, is negative 1.66. Negative 1.66. As you can see, the electrons do end up canceling. This is a balanced reaction. We then have these E naught values. So what is the overall cell potential? It is going to be the cathode minus the anode. So the cathode, right, minus the anode. So we get a positive 2.62 volts is the solution. So go ahead and try this one. Pause this video, try it, double check, make sure you got the right answer.